Isaac Newton, physicist, mathematician, astronomer, author. Oh, and that guy that developed the theory of gravity when an apple fell on his head. Among the many things that he is famous for, Newton formulated the 3 laws of motion that form the foundation of classical physics, and we're going to explore them today on Ask the Science Kid. Newton's 3 laws of motion describe the relationships between the motion of physical objects and the forces acting on them. Important quick definition. A force, in physics, is any external influence acting on an object that can affect its motion if it's not counterbalanced by a different force, typically explained as a push or a pull. This can be from something physical like my hand or the wind blowing, or it can be something less concrete, like gravity or friction, which are less direct actions and more like relationships between objects. Let's take a look at the laws. First law. An object at rest remains at rest, and an object in motion remains in motion unless acted upon by an outside force. This means that the hairbrush sitting on my desk isn't going anywhere unless something makes it. It's not going to move around on its own, no matter how much I insist to my mom that I don't know where it could have gone. It must have just gotten up and walked away. Likewise, in space, where there is no friction, a force, to slow this ball down, I could throw it, and it would fly forever in the direction I tossed it, unless it slammed into an asteroid or something. You experience this first law of motion every time you're on a moving vehicle. You know how when it starts moving really fast, you feel pressed into the back of your seat? That's because you are a body at rest and the car starts moving around you. You only start moving once the seat physically pushes you forward at the same speed as the rest of the vehicle. When the vehicle stops, you sway forward briefly because now you are a body in motion. The vehicle stops moving, but you continue forward at the same speed until something stops you. This is why it's so important to wear your seatbelt. Second law. Force equals mass times acceleration. There are a lot of concepts you need to understand in order to really play around with this one, and you need to be pretty good at multiplication and division, but ultimately, this law just states that there is a fixed relationship between how heavy an object is and how much force it takes to move it. The bigger the object, or the more you want it to move, the more force you will require. Likewise, applying the same force to a smaller object means it will go much further than the bigger one. This seems like a fairly obvious observation, but it is one of the most fundamental principles of physics, explaining things like gravity and enabling things like flight. Third law. You may have seen this written as for every action there is an equal and opposite reaction, but it might be more accurate to state it as for every force there is an equal and opposite force. This means that when I pushed that hairbrush with my hand, it was pushing back with the exact same force. You can feel this for yourself by pushing on a hard surface like my desktop. Now hold up. If the hairbrush is pushing back with the exact same force, then why does it move and I don't? We'll refer back to Newton's second law. I'm much bigger than my hairbrush, so the amount of force it takes to accelerate my hairbrush doesn't have much acceleration effect on me. A really great example of Newton's third law is when you drop something against a hard surface. It has to be a hard surface because soft surfaces can start absorbing forces and changing their direction, and that is way too complicated for this video. When I drop my pencil on the table, it exerts a force on the table. A force, by the way, that is equal to the mass of the pencil multiplied by its acceleration downwards. Thank you, second law. That force is equaled by the table, and it exerts an upward force on the pencil. And we already know that force is enough to move the pencil, so it bounces. Some of my favorite science activities are ones demonstrating Newton's laws. You get to do them yourself in the lab. For today's lab activity, you'll need several things. I'll put them up on the screen now. You'll need a cup or glass, some water, a coin, some paper, a 3-ring binder or other slanted surface that can become a ramp, a couple of balls of different weights, another small object or toy, a ruler, a film canister, some Alka-Seltzer or other effervescent tablet, some space outdoors, and an adult to supervise. It only makes sense to do the first law first, so put all your materials to the side except the cup, the water, the coin, and the paper. Pour some water into the glass. This will add weight to the glass and help hold it in place. If you use something like a coffee mug, the water might be less necessary. Place the paper over the top of the glass and place the coin on top of the paper so it's positioned in the center of the mouth of the glass. Now we're going to quickly pull the paper away and the coin drops into the cup. This is because the coin was the object at rest, and when the paper was pulled away, it stayed put. Now try pulling the paper slowly. It doesn't work because friction helps hold the coin in place long enough for the paper to start the coin moving, just like you in that moving vehicle. To demonstrate the second law, you'll need a ramp. Feel free to construct your own. I'm going to use a binder. You'll also need some balls of different weights, a ruler, and a small stable object like this block. Place the block at the edge of the binder along with the ruler. Start by rolling a lighter ball down the ramp and measure how far it moves the block. The force being exerted on the block is equal to the mass of the ball multiplied by its acceleration. And in this case, it moved the block 8 millimeters. Now let's try a heavier ball. The block moves further. This time, the force generated by the rolling ball is greater because although the acceleration is the same, it has greater mass. The effect of greater force on the same mass? Greater acceleration of the block. See if the pattern holds for other balls of different weights. Now for the demonstration I've been looking forward to showing you. We're taking the lab outside for this one. Bring your film canister, water, and Alka-Seltzer out with you. And your adult, of course. Fill your film canister about half full of water. Drop your tablet in, quickly secure the lid, and place it lid side down on the ground. Important safety note, do not stand over your rocket or point it towards anyone. Once you have placed it on the ground, back away to a safe distance. The buildup of carbon dioxide inside the film canister increases the pressure on the lid until it can't stand it anymore and it pops open. The force of the gases and water rushing out cause an equal and opposite force to be exerted on the film canister, launching it into the air. This is exactly how NASA gets its rockets into space, except with a lot more fire and explosion. Let's recap. An object at rest remains at rest, and an object in motion remains in motion unless acted upon by an outside force. Force equals mass times acceleration. And for every force, there is an equal and opposite force. Understanding these three principles means you're already well on your way to becoming an expert physicist. Congratulations! If you have questions you'd like answered or suggestions for a future video, send them to AskTheScienceKid@gmail.com, and make sure to subscribe to Ask the Science Kid for more fun facts and answers to kids' science questions.